I have to be honest with you. When I opened the folder for today's deep dive, I actually hesitated. I hovered over the open button on my laptop for like a solid 10 seconds, just staring at it.
Getting cold feet.
No, not cold feet. Just, I don't know, caution, a healthy sense of self-preservation, maybe? Because usually when we dive into a topic on this show, we're exploring history or, some new tech trend or a management philosophy, things where the ground feels solid. But today feels different. Today we are walking right up to the altar of modern physics. I'm talking about Albert Einstein, the golden calf of science, and we're essentially holding a sledgehammer.
It is a heavy swing, I'll give you that. It's not often you get a stack of sources that basically says, hey, everyone has been looking at this wrong for 100 years.
It's intellectually dangerous. That's the only way to put it. We are talking about special relativity. But, and this is why I hesitated, we aren't doing the usual thing. I refuse to do the usual thing. We are not going to spend an hour reciting textbook definitions or drawing those confusing light cones on a chalkboard that nobody understands.
Which is good, because this is an audio format and nobody wants to hear us derive partial differential equations.
Precisely. But looking at this stack of sources, describe this to the listeners, it's messy. It's chaotic. It looks like the contents of a mad scientist's hard drive that was recovered from a burning building.
It is an eclectic mix, to put it mildly.
Eclectic is polite. I'm looking at the file list right now. We have a series of PDFs with titles that sound like conspiracy thrillers. Einstein's Neglect, The Spherical Screen, Headshake Angular Velocity.
Very technical, but very specific titles.
Then we have a raw Python script, that Py file. And it's written for Is This Blender, the 3D program.
It is. Blender, the 3D modeling and animation software, usually used for making video games or Pixar-style movies, not checking physics homework from a century ago.
Okay, so we have PDFs, we have code for a cartoon maker, we have a breakdown of a YouTube video about something called information lag, and then sitting right on top of this pile of physics and code, we have a dense philosophical text on Jacques Lacan.
The French psychoanalyst.
Yes, the guy who reinvented Freud. Help me out here. How do we get from a Python script about light beams to a French psychoanalyst? Is there actually a thread here, or have we just lost our mind?
Oh, there is a thread. And it's a very strong, very surprising thread. But to find it, you have to be willing to accept a premise that sounds almost impossible at first glance.
Such is.
That the weirdness of the universe,
Right.
time slowing down, objects shrinking, twins aging at different rates, all that sci-fi stuff we associate with relativity isn't magic.
Yeah.
It isn't the universe physically warping like a piece of rubber. It's just lag.
Lag, like my internet connection is lagging. That kind of lag.
Information lag, exactly. The time it takes for reality to actually reach your eyes. The argument here is that what we call relativity is actually just a misunderstanding of how we process visual data on what these sources call a spherical screen.
Okay. I'm skeptical. I'm highly skeptical. Because you're basically saying that a century of physics is based on, what, an optical illusion?
Not an illusion exactly. An artifact of observation.
Well, that's the mission today. We are going to dig through this mad scientist stack and see if we can make sense of this worldview. We're going to look at deviation shooting, which sounds cool, and we're going to look at this Lacanian cut. But let's start at the beginning, the hub of the theory.
Let's do it.
We have this video summary, source 17EJ082. It talks about space-time distortion as information lag. Set the scene for us. What is the core argument here?
The central thesis is that space-time distortion is an apparent phenomenon.
Okay, hang on. You keep saying apparent. To me, apparent means a magic trick. It means it looks like the lady is sawed in half, but she isn't. Are you saying relativity is just a trick?
In a way, yes. Think about the difference between being and seeing. The source argues that the distortion is caused entirely by the delay in information transmission. We never, ever see the world as it is right now. We only see the world as it was when the light left the object.
Because light takes time to travel.
Exactly. Even if it's a nanosecond,
Yeah.
there's always a lag between reality, the thing happening out there in the physical world, and observation, us registering that event in here. The source uses the analogy of looking at a star.
Which is the classic example, right? If I look at Sirius, I'm seeing it as it was 8 years ago, or whatever the number is.
Right. If that star blew up 5 years ago, you'd still see it shining brightly in the sky today.
Yeah.
You were looking at a past image. That part is completely uncontroversial. Everyone accepts that.
Sure, I get that.
But this theory extends that logic to everything. Not just stars light years away. It applies to a moving train, a baseball flying through the air, or even your hand moving in front of your face.
So if I'm watching a train move across the horizon, I'm not seeing the train where it is, I'm seeing the train where it was a split second ago.
Precisely. And if that train is moving fast enough, or if the distances are vast enough, that lag becomes significant. The source argues that what Einstein called curved space-time or time dilation isn't the train physically changing its properties. It's simply the mathematical correction required to map that past image onto our current reality.
It feels like a mapping error, like when your GPS lags and it shows your car a block behind where you actually are on the road.
That's a great way to put it. And to understand how this mapping happens, we have to look at PDF081, this concept of the spherical screen.
Yeah, I read this part 3 times and I'm still trying to wrap my head around it. It says we need to imagine we are a camera eye. What does that mean?
Okay, close your eyes for a second. Imagine you are floating in empty space. You are a single point of consciousness.
Okay, I'm a dot, floating.
Now, how do you see the world? You don't see it in a square, like a movie screen. You see in every single direction, up, down, left, right. The visual world surrounds you completely.
Like I'm inside a dome, a planetarium.
Exactly. You are at the center of a sphere. This is the spherical screen. All external events, everything happening in the universe, are projected onto the inside surface of this sphere that's centered on you.
So my entire visual field is just a projection on a screen surrounding me, like I'm wearing a VR headset that covers 360 degrees.
Yes. Now, here is where the unit circle concept from PDF082 comes in. Imagine a train moving in the real world. It moves in a perfectly straight line.
Okay, straight track, simple.
But on your spherical screen, does it look like a straight line? If a train goes from the horizon on your far left, passes right in front of you, and goes to the horizon on your far right, on the inside of that sphere, it's tracing an arc.
Because the screen itself is curved?
Right. The distortion is just the math of translating a straight line in 3D space onto a curved 2D screen. And because of the information lag, the position of the train on that screen is delayed. The front of the train and the back of the train are sending you light from slightly different moments in the past.
Okay, I think I'm getting it. It's not that the train physically shrinks or that time physically slows down on the train itself. It's that the image of the train on my spherical screen behaves differently because the light from the back of the train and the light from the front of the train are reaching me at different times, and I'm projecting that onto a curve.
You've got it. The source calls this a reconfiguration of the data. And then PDS083 throws in a new variable that I think is fascinating. Headshake angular velocity.
That sounds like a dance move.
It does, doesn't it? But think about tracking that train. If you want to keep your eyes on it as it goes by, you have to turn your head.
Yeah, of course.
When the train is far away on the horizon, you turn your head very slowly. But when it passes right in front of you, you have to whip your head around really quickly to keep up with it.
Right. Whoosh, it zips by.
That speed of turning, that angular velocity, is actually how your brain perceives speed. The theory argues that the Lorentz transformation, the heavy, scary math of relativity, is actually just a formula to correct for these angular shifts on your spherical screen.
So it's not magic math, it's screen calibration. It's correcting for the shape of my own perception.
Ideally, yes. It's correcting for the fact that the signal is delayed and it's being projected onto a sphere.
Okay, I can visualize the sphere, I can visualize the lag, but we need to see this in action, we need to prove it. And this is where things get really nerdy in the best way possible. We have a source here that is literally a Python script for a Blender add-on.
The light clock simulator, yes.
Now, I'm not a coder. I know enough Python to be dangerous, which usually means breaking things. But I looked through this code. It's simulating the vertical arm of a Michelson interferometer.
Which is a mouthful.
It is. Let's just call it the light clock. It's the standard textbook example they use to teach relativity in college, right?
It is. The setup is simple. Imagine you have a flashlight on the floor and a mirror on the ceiling.
Yeah.
You shoot a pulse of light straight up. It hits the mirror and bounces straight back down.
Tick-tock. Up, down. Simple.
Right. Now imagine this whole setup floor, ceiling, flashlight is on a train moving sideways at a very high speed.
Okay. So the code setup here says, we have a system moving at velocity v dollars equals $0.11. That's 10% of the speed of light.
Which is incredibly, ridiculously fast.
And a light pulse is fired vertically along the z-axis to a mirror at height $1 equals $10.
Simple enough. If the train were stopped, the light goes up 10 units, hits the mirror, comes down 10 units. Total travel distance, 20.
But the train is moving. And the code has this fascinating feature called origin mode. I was playing with the logic of this. It lets you switch the origin, the zero point in space, between the floor and the ceiling.
This is a brilliant piece of UI design that actually explains a deep physics concept. It's all
Wow.
about reference frames.
Explain that. Why does it matter where I put the 0?
It's a toggle for simultaneity. If you set the origin to floor, you are saying the experiment starts now, here on the floor where the light is born. You are anchoring the entire universe to the start of the event.
Okay. My point of view is the flashlight.
But if you set it to ceiling, you are shifting your reference frame to center on the reflection event. You're saying the reflection is the anchor point of reality. The code essentially recalculates all the past coordinates based on that future anchor.
It's like switching camera angles in a video game. First person versus third person. The whole world reorients around your new perspective.
Exactly. And what happens to the path of the light in the simulation when the train is moving? This is the crucial part.
Well, this is the geometric reality, as the outline calls it. In the simulation, even though the light is fired vertically relative to the flashlight on the train, from an outside perspective, the path isn't vertical anymore, it's diagonal.
Right. Because the mirror is moving sideways while the light is moving up. The light has to chase the mirror.
It forms a triangle. The vertical path is one side, the horizontal movement of the mirror is another side, and the light travels the hypotenuse.
And we all remember from high school geometry, the hypotenuse is the longest side of a right triangle.
So the code shows that the light doesn't travel a distance of 10, it travels a longer distance, the hypotenuse distance.
And here is the punchline. Since the speed of light is constant, it cannot speed up to cover that extra distance in the same amount of time. What has to happen?
It has to take more time.
Exactly. If the distance is longer and the speed is the same, the time must increase.
So time dilation, this mystical idea that time slows down for people on fast-moving trains, is
Just the extra commute time for the light. It's the extra distance light must travel to catch the moving mirror.
It's not that time slowed down on the train, it's that the light had to run further to get to its destination.
That is exactly what this theory posits.
Yeah.
It aligns perfectly. The slowing is geometric. It's mundane.
Mundane. I don't know if I'd call it mundane. It changes everything. It means we've been mystifying a simple travel delay for 100 years.
Well, hold on. It gets more complex. Because now we have to talk about why Michelson and everyone else got so confused. We have to talk about deviation shooting.
Yes. This is the core metaphor of the whole deep dive. The Japanese term is hensa shigeki.
Which translates to deflection shooting or deviation shooting.
It sounds like something from a fighter pilot manual.
It is, essentially. And that's the perfect metaphor. The sources asked a very, very provocative question. What if the most famous failed experiment in history, the Michelson-Morley experiment, was designed based on a complete misconception of how we aim at moving targets?
Okay, let's unpack this. The notes break this down into 3 steps, and I really like this because it takes this abstract light clock and turns it into a sniper mission. It makes it visceral.
It really clarifies the fundamental problem.
Let's start with step 1, the easy one, the stationary target.
This is the baseline. Imagine the interferometer, our light clock, is stopped. Velocity 5 equals $1 equals standing in a field. You have a target directly above you at height 10.
Easy, point and shoot.
You aim your rifle, your light gun, straight up at the coordinates, $10. You shoot.
Bang!
Direct hit. The light travels up, hits the mirror at time, T at $. Simple. No lead required. You aim where the target is, you hit the target.
Okay, no brainer. Now we enter the danger zone. Step 2. The source calls this the World War II assumption.
This is the design phase logic. Now imagine that target is a plane moving sideways at 10% the speed of light.
A very fast plane.
If you were a gunner in WWII trying to hit a moving plane, you don't aim at the plane. If you aim where the plane is right now, you miss. Every time.
Because by the time the bullet gets there, the plane is gone. You have to lead the target, like a quarterback throwing to a receiver. You throw to where they will be, not where they are.
Exactly. So let's do the math that Michelson presumably did in his head when he designed his experiment. We know the mirror moves. We can calculate its future position. At time $10, the mirror will have moved from 6 to $6.01.
Right, because velocity is 0.1 and time is 10. Distance equals velocity times time. Simple math.
Right. So the design logic says we aim at the future point, $1, $10. We fire the light at an angle, expecting it to meet the mirror at that exact spot, at that exact time.
That seems reasonable. That's how you shoot down a plane. You calculate the intercept course. You say, meet me at coordinates XY at $10 p.m. sharp.
It is reasonable for bullets. or from footballs. But light is tricky, and this is where the source notes that this is predictive. It assumes we can prearrange the meeting point based on a fixed time, T dollars, $10.
Okay.
This is how the Michelson interferometer experiment was conceptually designed. He assumed the light would behave like a well-timed soldier arriving on schedule.
But then we get to step 3, the reality of light, or as the outline calls it, the breakdown. So why does this perfectly logical plan fail?
Here's the problem with step 2. Light has a constant speed. $1 equals dead $1.
Sure.
It doesn't care about your prediction. It doesn't know the future mirror position. It just travels at its speed in the direction you fire it.
So if I aim for that future point, $1, $10, I'm creating a diagonal path for the light, a hypotenuse?
Yes. And as we learned from the blender simulation, the diagonal path is longer than the vertical path.
Oh, okay, I see where this is going.
If the path is longer and the speed is constant.
It takes more time. It physically cannot get there in 10 seconds. It's impossible.
Exactly. The light is the quarterback who threw the ball to the right spot, but he threw it too softly. The ball is in the air, but the receiver gets to the spot, looks around, sees nothing, and just keeps running down the field.
So the light misses the meeting.
It misses the step 2 deadline. Look at the source material. I want you to look at the log file from the Blender simulations right there in the middle of the page. Tell me what the output says.
Okay, let me find it. Time t, here it is. It says time t 10.05038. In position x, 1.00504.
Look at those numbers closely. Step 2 predicted the hit would happen at time 2e pyrone and position 6 by Lillard.
But the reality is 2, $10 over 5 sum. It's late.
It's late. And because it's late, the mirror has moved further. It's not at position Z1 anymore. It's at 6 dollars 1.0055.
It's a moving target that kept moving because the bullet was too slow to get there on time?
Exactly. This is the insight of step 3. We aren't aiming at a future location that we can fix in time. We are aiming at a space-time event where the light finally catches up to the mirror.
And that event happens later in time and further away in space than the design predicted.
We cannot force the reflection to happen at $10. The universe doesn't care about our clock. We must wait for the event to establish itself.
This is mind-bending. Michelson set up his entire experiment assuming step 2 logic. He assumed I'll calculate the path and the light will hit at this exact time. But because of the simple geometry of a triangle, the light was always going to be late.
And because he didn't account for that lateness, that deviation, he interpreted the results as a failure. He thought the speed of light must be changing or the ether must be dragging it. But in reality, he was just missing the step 3 logic.
That really changes how you look at the concept of an error. It's not an error in the machinery, it's an error in the philosophy of time.
It's a category error, confusing a plan with a process.
But wait, if the light is taking longer to catch up, doesn't that imply something weird about speed? Section 4 of our notes brings up this concept of closing speed, and I have to admit, when I read this part, my Einstein police alarm went off in my head.
The Einstein police.
Yeah.
Freeze! You're violating causality.
Exactly, because I'm seeing numbers in the notes like 1.1 C or 1.41 C. That's 110% the speed of light. You can't do that. Nothing goes faster than light. That's like rule number 1.
You are absolutely right. Nothing, no object, no signal, no information travels faster than light.
Then explain these numbers before I have to arrest you for crimes against physics.
We have to understand the difference between object velocity and closing velocity.
Okay.
Let's use the analogy from the notes. The matchbox and the matchstick.
Okay. Set the scene for me.
Imagine a matchbox. It's sitting on the rail. The notes call this the Maxwell frame. This is the frame of the electromagnetic field itself. It's stationary. It's the backdrop of the universe.
Matchbox on the tracks. Got it.
Now, imagine a matchstick. It's on the train. This is the interferometer frame. It's moving at high speed.
Matchstick zooming by.
Now, the matchstick rubs against the matchbox.
Friction.
And it creates a spark.
Yeah.
An electromagnetic event. Light.
Flash.
Now, here's the zero relative velocity trap. For a split second as they touch, the matchbox and the matchstick are at the same location. You might be tempted to say they are together, but they belong to different worlds, different inertial frames.
Okay, one is moving, one is not.
Crucial rule.
Yeah.
The spark, the light that is created, belongs to neither object.
Whoa. Say that again?
The light does not belong to the matchstick on the train, and it does not belong to the matchbox on the tracks. The spark belongs to the Maxwell electromagnetic field.
It's an independent entity, like dropping a letter in a mailbox. Once it's dropped, it's not yours anymore. It belongs to the Postal Service.
That's a perfect analogy. Once that light is born, it follows the rules of the field, not the rules of the train or the tracks. It moves at speed 2/7 relative to the field.
Okay, I follow that. The light is its own thing. But what about the 110% speed?
That's the closing speed.
Yeah.
It's the rate at which the gap between two things changes. Let me give you a simple car example.
Please.
Imagine you are in a car driving west at 60 miles per hour. I am in a car driving east at 60 miles per hour. We are on the same road driving toward each other for a head-on collision.
A dark example, but okay, I'm with you.
From my perspective behind the wheel, how fast does it look like you are coming at me?
Well, if I'm doing 60 and you're doing 60, the gap is closing at 120.
Right. The gap between us is closing at 120 miles per hour. But is your car's engine actually capable of going 120?
No. My speedometer says 60.
Is mine.
No, you're doing 60.
Exactly. The gap closes at 120. But no object is moving that fast. The source argues the same thing happens with light.
So if a light beam is moving left at speed, $60.
And you are on your train moving right at speed, $0, $1 towards it.
Then the gap between me and that light beam is closing at $1, $1.
Correct. 110% of the speed of light. That is the closing speed.
And that's allowed. The Einstein police aren't going to bust down my door.
It's perfectly allowed. It's just geometry. It doesn't violate causality because no information is traveling that fast from point A to point B. It's just the rate of separation decreasing.
Okay, I can breathe again. Physics is safe.
But here's why it matters for this entire deep dive. In the interferometer frame, when we are sitting on the moving train, we must calculate this closing speed for light coming from different directions.
Because if I'm moving into the light, the closing speed is higher. But if I'm running away from the light, the closing speed is lower.
Exactly. And the source argues that special relativity, all those complex formulas Einstein wrote, is really just the mathematical result of these direction-dependent closing speeds.
So Einstein's math is basically a way to normalize these closing speeds so they all just look like C from our perspective.
That's the argument. It's saying, since our biology and our instruments can't perceive the closing speed directly, our math adjusts the time and distance variables to make the result constant.
It's the spherical screen auto-correcting again. It's all trying to make the universe look consistent for my little camera eye.
It's all connected.
This is heavy. I feel like I need to lie down.
Well, that's appropriate. Because for the final section, we are going to lie down on a psychoanalyst's couch.
Ah, yes, the Lacan connection.
Lipicanian cut.
I have to admit, when I saw this in the outline, I thought it was a typo. We've been talking about vectors and closing speeds and Python code for an hour, and suddenly, psychoanalysis.
It seems completely unrelated. What does a French psychiatrist from the 20th century have to do with photons?
But then I read the source, and the parallel is, it's kind of haunting. It's shockingly clear.
It is. It's all about how we treat time.
So break down the difference between Freud and Lacan for us. I know Freud is the tell me about your mother guy.
Right. But think about the structure of a Freudian therapy session. It is the standard 50-minute hour.
You lie on the couch, you talk. At 50 minutes, a buzzer rings. Session over, time's up.
Even if you are right in the middle of a breakthrough. Even if you are crying or finally realizing something profound about your childhood. Doesn't matter. Time is up. See you next week.
Time rules the process. The clock is God.
Exactly. In the Freudian model, the clock is the master. You interpret the content after the time runs out. The duration is fixed and arbitrary.
Okay. And Lacan.
Lacan was a radical. He was the punk rocker of psychoanalysis. He introduced the variable session length.
Variable.
He didn't care about the clock. He cared about the event.
The event.
The moment of truth. The realization. The slip of the tongue that reveals everything. He called it the scansion or the cut. The analyst cuts the session the moment a significant truth or event occurs.
So the session might last 5 minutes or an hour and a half.
It might last 5 minutes. It might last 2 hours.
Yeah.
The session ends when the thing happens, not when the clock says so.
It's result-oriented timing, not schedule-oriented timing.
Exactly. Now bring that back to physics.
Oh, wow.
Do you see it?
Step 2, deviation, shooting the old physics. The Michelson design is Freud.
It is Freud. Think about it. We decided the experiment ends at TT $10. We set a fixed 50-minute hour. We tried to force the light to fit this timeline. We said the reflection must happen at TT $10 because that's what the schedule says.
And when the light didn't show up on time, we had a crisis. We thought reality was broken. We invented all this weirdness to explain why the patient wasn't cooperating with the clock.
Right. But step 3, the new insight, the reality shown in the blender simulation, is Lacan.
Because the session, the light's journey, only ends when the event happens.
Precisely. The light hits the mirror at $10.05. That is the Lacanian cut. That's the moment of truth. The universe waited for the event to establish itself, independent of our schedule.
The oversight of Michelson was that he assumed a Freudian fixed time for his experiment. He wanted the universe to run on a 50-minute hour.
But the universe operates on Lacanian variable time. It operates on event time. It waits for the connection. It lets the journey take as long as it needs to.
So simultaneity, the idea of two things happening at the same time, is not a pre-designed condition?
No, it's a result. It's a result that must be calculated based on when the event actually occurs in the field. You can't force simultaneity. You have to wait for it to happen and then work backwards.
That is profound. It turns a physics problem into a philosophy of patience. It's saying, stop looking at your watch and watch the ball.
It really does. It suggests that we are often too busy looking at the clock, our predictions, our models, our schedules, to see the reality of what is actually happening right in front of us.
So, bringing this all back home, we've gone from a spherical screen where we watch the past, to a blender simulation where light misses its appointment, to a psychoanalytic couch where time is variable.
It's quite a journey.
Let's synthesize this. The core takeaway seems to be that the distortion of relativity, all the weird stuff, isn't the train physically morphing or clocks physically slowing?
No. It is the information lag inherent in step 3. The light takes longer because it has to catch up in the Maxwell field. The geometry of the situation forces a longer path.
And because the path is longer, the arrival time is delayed. And that delay is what we measure and call time dilation.
That is the argument. It's simpler in a way. It removes the mysticism and replaces it with geometry and lag.
It makes the universe feel a little less like a Salvador Dali painting, all melting clocks and weird shapes, and a little more like a really complex, laggy video game.
Which, depending on your perspective, is either comforting or terrifying.
I'll go with fascinating. It implies that the math of relativity works, but our story about what the math means might be wrong.
Exactly. The equations aren't wrong. The map isn't wrong. But maybe we've been reading the legend upside down this whole time.
Before we wrap up, I want to leave our listeners with that final provocative thought. You mentioned something earlier that really stuck with me.
Sure. I want you to consider this. If Michelson had used step 3 logic, if he had sat down and calculated the specific Lacanian arrival time for each arm of his interferometer separately, if he had expected the delay because of the geometry, would the failure of his experiment have actually been seen as a perfect confirmation of this information lag model?
That's the kicker.
Did he actually succeed but just use the wrong answer key to grade his own test?
That is something to keep you up at night. Sometimes, to see the truth, you have to stop looking at the clock and start looking for the event.
Well said.
Thanks for diving deep with us. This was a wild one. We'll see you in the next event.
Goodbye.
See ya.